Hello, in this video we begin our study of linear maps, first asking what they are. One of the things that linear maps do is to preserve relationships. We've already seen two maps that do this, and linear maps are similar. A GPS road map preserves the geometric relationships between roads. If two roads intersect on the GPS screen, we expect they'll intersect in the real world. For the circle for each state corona detection count map, it preserves the numerical relationships between the numbers of people with the coronavirus. Now, linear maps are maps between vector spaces. They preserve the linear relationships between vectors. Here's an example. Let's suppose that one vector, v2, was equal to 3 times another vector. Well, if a map F from, say, V to W is linear, and this is a relationship between two vectors in V, then since V is linear, we expect that, let's start with the other one to keep the orientation right. Okay, we expect that the image of V2 is going to be 3 times the image of V1. Now, the image of V2, f of V2, and the image of V1, f of V1 are members of W, so we expect that this relationship will be maintained between the original vectors and their images. Okay, let's look at an example. Well, first let's look at the linear map definition. Okay, here's the definition of a linear map. A linear map F from V to W with both V and W vector spaces sends each sum of domain vectors, V1 and V2, to the sum of their codomain partners, so that f of V1 plus V2 equals f of V1 plus f of V2. And also, for any vectors V and numbers R, the map sends the rescaled vector in V to the rescaled partner in V of V in W. So that means that f of R times V is equal to R times f of V. Well, let's see how that works out in an example. So this is going to be a map that's a linear map for V being any vector space, except for the fact that we're having V be a map from V to V, so the codomain is equal to the domain. The pairing is V is paired with 7 times V. Okay, so the first question is it a map? Well, if it's a map, this property has to be true. So we'd like to verify that it's true. We have to verify it for all members of V1 and V2. And the way to do that is to choose typical values that their only property is they're members of V. So we can only use the general properties that are true of all vector spaces. Since we have to show that a conditional is true, we want to assume the premise. So let's assume that the arbitrary or typical vectors V1 equals V2. And we have to show that their images are also equal. Well, if this is true, let's start off by considering f of V1. Well, according to the pairing, that's equal to 7 times V. So this is equal to 7 times V1. And because V1 equals V2, that's equal to 7 times V2. And in fact, the pairing of the image of V2, f of V2, is just 7 times V2. So this is equal to f of V2. So this shows that if I start off with two vectors, V1 and V2, they can't have different images. So this makes it into a map. Okay, let's consider now whether this map is linear. We have two properties. The first one is shown here. Let's consider the left-hand side. F of V1 plus V2. Well, according to the map, the partner of v1 plus v2 is 7 times that vector. So it's 7 times v1 plus v2. And one of the properties of vector spaces is that scalars distribute over vector addition. So this is equal to 7 times v1 plus 7 times v2. Now, f of v1, the partner of v1, is 7 times v1. So this is equal to f of v1 plus, and the partner of v2, f of v2 is 7 times v2. So this is the partner of v2. And that verifies that this property is true. So we have the first property. Now let's look at the second property. Okay, we have to show that f of r times v equals r times f of v. Well, let's consider what f of rv is. We know the pairing, that f of v equals 7 times v, so this is 7 times rv. Now, these multiplications in here, according to the properties of vector spaces, are associative. So this is equal to 7 times r times v, which equals r times 7, because numbers are commutative, times v. And this equals, in turn, using again the associative property of these operations in vector spaces, r times 7v. We're taking baby steps here. Okay, that's r times, and 7v is the image of v, so this is 7 times f of v. Okay, so check. This map is linear. We can check now, is it one-to-one? Then we'll check, is it onto? So if it's one-to-one, then the property we need to verify is that if for any v1 and v2, f of v1 equals f of v2 implies v1 equals v2. So let's take v1 and v2 typical or arbitrary values and assume that f of v1 equals f of v2. And we need to show now that v1 equals v2. Well, we can say, because this is true, and we know that f of v1 equals 7 times v1, since that's equal to f of v2, and f of v2 equals 7 times v2, we know that 7v1 equals 7v2. We can multiply both sides of this equation with 1/7 and cancel off the 7 to obtain v1. That's basically a result of the properties of vector spaces. We can verify that v1 equals v2. So in fact, this map is one-to-one. There's no way that these could have come from different vectors. Okay, let's check the last property. That is this map onto. Well, the onto property that we need to verify being true or false is that if it's going to be onto it, for every W member of the codomain, here the codomain in fact is the equal to the domain, so this W is a member of V. So let's choose W to be an arbitrary vector in the codomain, that's V, and then we have to show that there's another vector V such that W equals f of V. Well, let's choose, we just have to, since we have to show it exists, we just have to choose one. Choose V equals 1/7 W, okay? And then we have to check that f of V, which equals f of 1/7 W, and according to the pairing, that's 7 times 1/7 W, which equals W. So that means that all we have to do is, to find the preimage, or the vector that maps to W, all we have to do is select 1/7 of W. And that shows that this map, for any vector space, is linear and one and onto.